I hope everybody is fine. We'll continue with our class, and in our previous class, we were discussing the Himanshu. Just keep your camera off. The link layer took the error detection error in which took the parent one parity to be and it takes. Today's will be discussed protocols. I'll share the. Do you have any question for this one? Just off the so that I can say on. If I am I clear now? Okay. Fine. Is my voice also clear? If I was not able to listen to me. All right. So let me start then. So after the error detection correction, the first one was framing. How does the services that is provided by the data link, how does it actually make the frames? The second one is how does it actually check the errors and detect the errors. Today's lecture would basically deal with multiple access protocols. And to understand what multiple access protocol is, let me go back to this slide. Which there are two types of links. One is the point-to-point link, PPP. Like we had two connections in which I said that, like I'll see an example of that. That is high-level data link control. PPP, we do not need much of a protocol because there are just two people. Like Ramanan and me discussing, Ramanan stops, I'll start speaking. I'll stop and Ramanan would start speaking. So we wouldn't require much of a protocol to control. As compared to that, if we take a class with 60 students, if everybody starts to speak, it's a broadcast channel, everybody is allowed to speak, then we would have a problem in that case, wherein everybody would be speaking and what we would receive would be just the noise. So in that case, in the shared medium or a shared wire, wherein we have broadcast link, we have multiple senders as well as multiple receivers. All would be connected through the single common shared broadcast channel. This also means that when any node transmits a frame, the channel broadcasts the frame and each of the other node receives a copy. The examples of these broadcast links are Ethernet and wireless LAN. So in these cases, what we require is multiple access protocols. And what do these multiple access protocols do? They coordinate the access of multiple sending and receiving nodes in the shared broadcast channel, typically used in LANs. It will ensure that collisions are not there, or if collision happens, what to do. If simultaneously two senders send, what would happen, and so on. So these are all decided by the multiple access protocol. Like, for example, in class, to stop everyone speaking, we would use some kind of protocols in which we will make sure that there is no noise. Like, I will give everybody a chance to speak, but do not speak. I give you a chance to speak. Somebody speaks, don't continue to speak for so long. Give others a chance as well. If I am speaking, I'll say in the class, raise your hand. I would get to know that, yes, you have a question to speak. I'm speaking, don't interrupt till I stop. Okay? And things like that determine how we, communicate with the class. And likewise, similar to this, in computer networks also, we have the protocols known as multiple access protocols. Now, since we are discussing about those nodes who are capable to transmit frames, number one, who are connected to the link, same broadcast link, number two, right? And they can receive the frames at the same time. Now, if two nodes simultaneously start a transmission, what happens is the signal collides with each other. And due to this collision, you would get an erroneous data, or you would have problem in getting the data itself. Typically, if frame collides, then that frame is lost. So this is what is basically multiple access protocols. And to understand this, we have a given channel. Let me see. So we have three broad categories of multiple access protocols. The first is the channel partitioning protocol. In this, what you do is you divide a channel smaller pieces like time slots or time frequencies. And then what happens? Each of the node that wants to transmit sends a piece of information or a frame during that slot, or you divided it based on frequency and so on. The second one that we have is a random access. We do not divide the channel as per time or frequency. We allow everybody to use the channel. And if collision happens, we recover from collision. And the third one that we have is taking turns protocol. In taking turns protocols, it's like round robin. Okay, everybody gets a chance to speak. And what are we looking at? Ideally, multiple access protocol for a broadcast channel of rate R bits per second. This is the data rate that we can have in that channel. Should have these desirable circumstances. That when only one node has the data to send, node has the throughput of R bits per second. This is not, this is actually desired data rate, what we want it as such. So if R is the data rate it can send, we should get the maximum throughput, that is R bits per second, when it's only one node. But if there is one node, let's say M nodes, they have to send the data, then each node should get the throughput of R by M bits per second. We want a protocol number 3 that should be decentralized. Decentralized, no master slave coordination. Centralized is master slave coordination. We do not want that. Why? Because we know with master slave, there is a single point of failure. If master fails, the whole of the system fails. It will bring the entire system down. We don't need a special node that would coordinate it. We don't need synchronization of clocks and slots and so on. And it should be lastly simple in expensive to implement. Let's go to the first one. Before that, we will add a slide here before this. And I will say here we have multiple access protocols, and in this there are three. Ramanand, what are you seeing? Okay, that's fine. So we have three of these random access protocols. The second one that we have is controlled access protocols, and the third one that we have is channelization protocol. All right, these are the three protocols that we have, three broad categories of protocols. And within this, let me just, so this like here. And within this, we have for random access protocols, the first one is Aloha, the second is CSMA, the third is CSMA CD, and the fourth one is CSMA CA. Likewise, in controlled access protocols, we have three. Number one, reservation. Number two, polling. Number three, token ring. And for the channelization as well, we have three. The first one is FDMA. The second is TDMA. And number three is CDMA. Okay. So this is the categorization that we see of multiple access protocols. The broader one is random access, controlled access, and channelization. And each one has their own set. Now to begin with, let's first take the third one, that is the channelization protocols, in which we have FDMA, TDMA, and CDMA. And begin with, you understand what basically TDMA, FDMA is. We discussed it in few classes back as well. In this case, what we do is, if it's TDMA or it's FDMA, what we do is, let's say first FDMA. This is frequency division multiple access. Okay. What we discussed in the previous class was FDM. Remember? uh, there is a difference between FDM and FDMA. This we are discussing frequency division multiple access. The previous one when we discussed was frequency division multiplexing. Conceptually they look same, but it is different here. Why? FDM, we studied FDM in physical layer. So FDM, frequency division multiplexing, is a physical layer technique where we combined loads from low bandwidth channel and transmitted them by using a high bandwidth channel. And the channel that are combined are low pass. We used a multiplexer which modulates the signal, combines them and creates a band pass signal. Fine. But what is FDMA here? FDMA is an access method in data link layer. So conceptually the working may be same, but they are at a different layer and the purpose is different. Data link layer tells physical layer to make a band pass signal from the data passed to it. Then the signal must be created in allocated band. So two fundamental differences that you see here in the name itself. One is multiplexing, another is multiple access. Multiplexing deals with how multiple signals can utilize a single source. For example, you might have studied about sampling, modulation, etc. That comes under multiplexing. But here, multiple access deals with which signal can utilize a particular resource at a particular time. For example, frequency, time, and so on. So basically, multiple access would deal with which signal can utilize which particular resource. Is this part clear? Okay. Any question? I hope you understand the difference between FDMA and FDM. In physical layer, if we see there is no multiplexer in FDMA because data link layer tells the physical layer to do this multiplexing. So in other words, we can say FDMA would allow multiple users using FDM. So FDM is used to achieve the goal. Now let us understand what basically FDM and TDM is. Time division multiple access and FDM, they both partition the channel like this is given in the figure below. They break the broadcast channel into slots. In case of time, we have time slots. So a channel can support n nodes and the transmission rate of the channel would be R bits per second. How it can be R bits per second? Because during that time slot, it gets full bandwidth, it gets the full transmission rate. Because if in the figure you can see blue is transmitting here, let me, if you can see here, okay. If you can see in the figure here, the blue one, right, it gets a time slot. This is a link in which there has been 6 stations and 6 stations get a slot each. So after every 6th one, the first one would get another chance here. Now, during this time when the first gets the chance, During this specific period of time that I'm annotating here, only one node is transmitting, that is node number one. That's why when it transmits at the rate of R bits per second. So TDM divided time into time frames that you see. This one, this is a time frame. And each time frame is further divided into n slots. So we have here 1, 2, 3, 4, 5, 6, 6 slots. Now, this frame, again, there might be confusion here. We are talking about a frame here. And till now in data link layer, whatever we talked about frame, it was the protocol data unit and PDU of data link layer. We call them as frames. This frame is different. This is a time frame. That frame is PDU, protocol data unit frame. So make sure you do not confuse the two. This is what we are speaking about is time. Now, generally, here you see there are 6 slots. Generally, this slot is chosen such that during this time, that is the time that it got for one, that is I'm showing in the red. During this specific time, one frame of data link layer should be transmitted. It's typically chosen such that, so that you don't have to partition the frame and send the half of a frame here and then half of the frame here. I repeat, we have a frame here in TDM MA. This frame is a time-based frame. You break them into slots, and size of each slot is chosen so that single packet or a single frame of data link layer can be transmitted during that time slot. Okay. Now, what are the advantages here that we see? It's a multiple access protocol. If we have 6 stations to send, all 6 would get an equal chance and a fair chance. Good. Also, there won't be any collision. Why? Because the sender would know that at this specific time I have to send. There would be synchronization there that okay, next, and so on. Then one would get chance in the next time frame and the next time frame and so on. So it eliminates collision. Everybody gets a chance. It's fair. But obviously it has also, if we see during that time slot when one is transmitting, the data rate at which one would be transmitting would be R by N in that time, where N are the number of nodes and R is the transmission rate of the channel. But it has some major drawbacks as well. The first one is that there were 6 stations who were connected to the what you call broadcast link. Let me clear this. Okay, you can see here 6 stations are connected, 1, 2, 3, 4, 5, 6. However, all I have the capability of transmit and receive packets, but however, during this period of time, only 3 of them were active, which is given by 1, 3, and 4, blue, red, and green. The rest of the 3, that is 2, 5, 6, were sitting idle. Once the other nodes did not have to transmit anything, the slots were empty. And because of this, we wasted some slots, and Also, the nodes 1, 3, 4 had to wait for its turn, even when others were not sending. And now, in this case, if only one transmits, other two also do not transmit. Let's say these two also not transmit. What would happen here? Node must always wait for its turn, even when it is only one node to send. It will still give a chance, empty, 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 and then one, empty, 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 and one, empty, 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 and so on. So it would waste the time. And that's why node is limited to the average rate of R by N, that is R by N, where R is the transmission rate of the channel, N is the nodes that are sending, because we have divided the time slots in N. All right. And this would be even when R by N is still the transmission rate, even when there is only one node to send. It will still have R by N, where N is the number of nodes that are connected to the link broadcast. Compared to that, the second one that we have is FDMA, that frequency division multiple access. Now, it basically is a channel spectrum division protocol in which you divide it into frequency bands. Each station is given or assigned a fixed frequency band. Like it's shown here in the figure, we have let me clear the annotation. We have FDM cable, all right? Then we give different bands here. You can see 1, 2, and 3. And then they get to transmit at the same time through this. Now we have this channel which was divided into 1, 2, 3, 4, 5, 6. 6 frequency bands. So FDM would divide R, if R is the carrying capacity, into different frequencies, and each would have R by N bandwidth. Okay. Now you can see in between the frequency bands, there is a line. I would depict this line with a green color here. Okay. You might have studied in FDM also. These lines here in green depict guard bands. I'll just write it here. GUARD, guard bands. And what are these guard bands? It's like, a zone between the two frequencies which separates the two. One frequency is separated from another frequency with a small band of which is known as guard band. Now in this channel partitioning, if we have 6 nodes, each 6 of them would get one of the frequency bands that are given here, like this one. So we assign each frequency to one of the N nodes. And at the same time, we can send, at the same time we can send, 6 of them can send. But it has advantages and disadvantages, typically that of TDM as well. That is, advantage would be that yes, you divide it, you can have multiple access, there won't be collision. Fine. But among the 6, again, if only blue, red, and green are sending, 3 of the frequencies go wasted. They are not used, they are not utilized. And also, since it's a channel partitioning protocol and it has divided the frequency into bands, if 6 of them are there, the overall bandwidth is reduced to R by N. This is the second disadvantage that we have. Then we move to a third one. It's not mentioned here. Wait. How do you slide here? So third one that we would be doing is CDMA, which stands for Code Division Multiple Access. CDMA. Okay, Ramanand, what do you see? Okay, fine. All right. All right. So the third channel partitioning protocol is CDMA, Code Division Multiple Access. And what it does basically, it assigns different code to each node. And then each node uses its unique code to encode data, bits, and cents. Okay. By this, different nodes can transmit simultaneously. So what basically we did in this protocol, that is CDMA, each bit is sent by the sender in an encoded form. That is basically it's encoded by multiplying the bit by the signal. So you multiply the bit by the code, that is the signal that you have. And that is at a much faster rate, which typically know as a chain rate. And it's a form of spread spectrum signaling, basically. And what you use is a modulated coded signal, which can have a much higher bandwidth. So CDMA, as the name itself says, code division multiple access. You have the data, multiply it with the code, and this code is unique to it. And then you send the signal. And everyone would have this uniquely sent signal, and they can simultaneously send the signal through the modulated coded signal. And this modulated coded signal has a much higher bandwidth. Then we move to the third one that we have here. And this one is random access protocols. Random access protocol basically transmits at the full rate of the channel. Till now we saw R was divided among the number of sending nodes. But when you talk about random access, the name itself says that there is no coordination among the nodes. They randomly send it across. Okay. And then what happens when two or more send at the same time? Collisions occur. But if collision occurs, what do? They try to resend it. And they will keep on trying to send until they ensure that the packet has been received without collision. When the collision happened, what does the node do? It's not necessary that the node retransmits at the same time. No, it can wait. And how much it can wait? There's a random delay before the frame starts to transmit once again. So random access MAC protocol specifies how to detect collision and how to recover from collision. That is when I said you transmit after a certain specific delay. Okay. For CD, let me go back to the previous one. People have not understood CDMA well. Okay. To understand CDMA here, I'll give an example to understand CDMA, code division multiple access. What CDMA is, or let me finish CDM. Let me finish this one, and I'll come back to CDMA. No, let's just finish CDMA first. So what basically CDMA here is, it is communication with different nodes. I'll give an example to understand. It's like, to understand this, when I said how can we transmit, simultaneously, okay? It's like in our class, okay? I'll speak to Ramanand, you speak Tamil, right? Telugu. Okay. It's different, right? Okay. For us, we all think that from South, everybody speaks Tamil. Okay. Okay. Who is your state mate? Molly? Okay, Molly and Abhinandan. All right. Within this class, you, Ramanand, would speak to Molly in Telugu. I would speak to, let's say, Arifa in Kashmiri. All right. And parallelly, you two are speaking, and I'm also speaking with Arifa in Kashmiri. You could easily communicate with him, and I could easily communicate with her because we used a different, language to speak. Though the space was common. That is basically what is CDMA. Now we have, let's say, 4 explaining this in terms of networks. 1, 3, and 4. We have a same channel. We have data D1, D2, D3, and D4. Each of them has been assigned, each of the channel has been assigned C1, C2, C3, and C4. And what is this? This is a unique code. C1 is of first station and it's unique to it, and it's different than what C2 is, that is of second. And they have 2 properties of codes. The first property that we have is, if we multiply each code by another, we get 0. And number 2, if we multiply each code by itself, if we multiply this, we get 0. And if we multiply each code by itself, we get 4. And what we have 4 here? The number of stations, the total stations that we have. Now send the data. What does station 1 do? It multiplies data by the code. Data is D1 multiply by C1 and so on. Station 2, D2, C2, station 3, D2, C3, station 4 default dot dot dot. Now, how does data go in channel? It would be D1 into C1 plus D2 into C2 plus D3 into C3 plus D4 into C4. Okay. Now, when this data goes into the channel, the data here is broadcasted. When the data is broadcasted means each channel would receive this data. When any station that receives the data from other three channels, what does it do? Now we are talking about the receiving side. All right, here, receiver. So any station that receives the data from one of the other three multiplies the data. So receiver multiplies the data by the code of sender. What do we mean by that here? If station 1 is sending to station 2, station 2, in other words, station 2 wants to hear what station 1 is sending, but the data that the receiver station 2 got here has the data of station 2, 3, 4 as well, because it's sent all together. Now what it does, it multiplies the data on the channel, that is this, one. It multiplies it, oops, where did it go? I think it's gone somewhere. Anyhow, I don't know where it's gone. But anyhow, now we know what we have the data here. We multiply that data of the channel by the code of the station C1. So receiver is station 2. Multiply data, the long one that we had, with code, the unique code of station 1. So what do we get here? As per the rule that I mentioned just now, the properties, if we multiply each code by another, we get 0. If we multiply each code by itself, we get 4. So what will we get here? C1 into C1 as 4. But C2, C1, C3, C1, C4, C1, they are all zeros. And then the result is divided by 4, that is the number of stations that we have, and thus we will get the data. Remaining would be data from station 1 received by station 4. I hope this is clear. I hope for those who had doubt with CDMA, this example would have cleared the doubt. Everybody? So CDMA is actually based on coding theory, because each station is assigned a code, which is a sequence of numbers known as chips. They are not chosen randomly, they are specific sequences. They are also called as orthogonal sequence. We do orthogonal sequencing here. So I'll move back to what we were discussing here. I hope this is clear, CDMA now. All right. So we move to now back to random access protocols. And now random access, we just now discussed that you start transmitting without actually caring who else is transmitting. And then if it's collision, it will start to retransmit. Based on some delay, it will start retransmitting again. And delays again are independent. If two of nodes collide, some of them can retransmit instantaneously, some can wait for a specific, independently, randomly chosen delay. Among this, we have three of them. First one is slotted aloha, the second one is aloha, and third one is CSMA. Fourth is advanced version of CSMA CD and CSMA CA, where CD is collision detection, and we are coming to each one by one. So slotted aloha. There are some assumptions that we take in slotted aloha that are that all frames are of same size. That means all frames exactly consists of L bits. Time is divided into slots of size L by R seconds. Nodes start to transmit frames at the beginning of the slot. Or to understand, slotted aloha, first let me go to pure aloha, because this is an earlier form, and then we got to slotted aloha. Pure aloha is also known as unslotted aloha. What does it say? Slotted, unslotted aloha says that when a frame arrives the data link layer, obviously from the network layer, node would simply push on this frame onto the link. That's immediately transmit the frame in its complete entire form onto the broadcast channel. There are two things that can happen. Either it can experience a collision or it can have a successful transmission. If the node collides, that's given here, if the node experiences collision, the node would immediately retransmit the frame with the probability of P. Or the node waits for some time for transmitting again. How much time? It can be the frame transmission time, that time that it has taken for the whole frame to be transmitted. After it has waited, it transmits the frame with the probability P, or waits for another time frame with the probability 1 minus P. To understand this, Raman, you can take the attendance as well. To understand this, let's go back to the slotted aloha. Now, some assumptions that we took here is that equal sizes frame, time is divided into equal slots. So equal slot here means that if you want to transmit one frame, you would require a single time slot to send. You do not break a frame and send half frame in one time slot and half frame in a time slot. Another thing in slotted aloha is that when we say slotted because you have broken the time as per frames and you send each slot at the beginning of the time frame. So if this is the time frame that I have, this is broken into specific time slots. How is this time frame different than TDM's time frame? Both have one thing common, that within this time frame, that is within this one, we can send one frame. Within one frame, within one time frame, we can send one protocol data unit frame. But within TDM, each of the node is given one specific slot. As compared to this, in Aloha, any node who has to transmit would start transmitting at the beginning of this time slot. Now what would happen here? Now what would happen here? At the beginning of the time frame, let's say here, if collision occurs, so both the senders, the node 1 and the node 2 could not send. Then we have the next time frame, that is this one. In the next time frame, again the probability that is between 0 and 1, in which node 1 can wait randomly till the next slot and 2 decides, no, I will send now. In this, we have a successful slot, a successful transmission. And the next one, node 1 had to send something, but you have not able to write. You can have empty slots, you can have collisions, and you can have successful slots. This is how we see in this figure. See, this explains the slotted aloha. The line here CES denotes collision, empty slots, and S as successful slot. Each of the frame is started at the beginning of the time. Now 3 nodes, node 1, 2 and 3 start to transmit at the same time, that is this one. What happens here? Collision happens. When the collision happened, there was no successful transmission. We have C here. All the 3 nodes randomly decide that, okay, we will not send in the next one. So what happens here? In this case, we have an empty slot E. Node 1 and 2 decided to send in the next one. Again, collision occurred. Then this is a cross. After this, node 1 decided that I will send after 2 slots. Node 2 decides that I will retransmit at the same instance. And in that case, we have a successful slot given by S. That is how it goes on. There will be collisions, there will be empty slots, there would be successful slots. Accordingly, we would have some disadvantages and advantages. And the advantages that we have is when a single node, let's say node 2 successfully transmitted, it was the only one using the channel. So it had a full transmission rate of R. This TDM. It was also divided into times, but the time slots were divided among n number of nodes. So in that case, in case of TDM, it used to be R by 3 here. But in this case, it would be R, even though there are 3 nodes that are transmitting. So the good thing is that you will get to transmit at the full rate of the channel. Second thing is it's decentralized. Nobody is controlling these slots. Okay. Anybody can transmit whenever they want. And the third thing that we have, it's simple to implement. Simple and inexpensive to implement because you just have to start to transmit. You just have to ensure that you start transmitting at the start of the time slot. But there are disadvantages as well. Like you see in the picture, among so many slots, the one which I have rounded here and the other one which I will round here, these are the 3 successful slots that we had among 1, 2, 3, 4, 5, 7, 8, 9 slots. So there is collisions, that is you waste a slot. There is empty slots, idle slots, that's again wasting of slots. Okay. And another thing is that clock synchronization is required. And why do we need? Arifa, am I audible now? Okay, fine. Another thing that we see here is clock synchro. What is clock synchronization? This is the start. This is the start. This is the start. This is another start. This is another start. All these beginning of the time slots are to be synchronized. What I mean by synchronized, it's like when node 1, 2 and 3 started at this time 0, they knew that this is the beginning of the slot. How did they know that this is the beginning of slot? This is how it's done by clock synchronization. And also, if I wait, how many slots I wait? 1, 2, 3, 4, 5, for example. And then this is the new slot. How would I get to know? Again, this I would get to know by set clock synchronization. So it needs clock synchronization as well. Then we have the efficiency of slotted aloha. What do we mean by the efficiency here? The fractions of successful slots out of the slots that we have across denotes the efficiency. Slotted aloha obviously would work perfectly when there is only one node to it will get the full rate without actually wasting the unnecessary slots. What were the unnecessary slots that were there because none of collision? And another fraction of slots were empty. Why were they empty? Many nodes had faced collision. They refrain from transmitting. Why? Because this is the result of probabilistic transmission policy. I'll write it here. Transmission policy. And what is this probability? It's like the slots that were empty because many active nodes who wanted to transmit refrained from transmitting because they had faced a collision. So they randomly waited for some amount of time. This is based on probabilistic transmission policy. And now we have n nodes and each transmit in a slot with a probability of p. Based on this, we will get this maximum efficiency that we can have. And it says, at the best, the channel used for useful transmission is 37% of the time. So if we have n active nodes, the efficiency of slotted aloha is p1 minus p to the power of n minus 1, where n is nodes which have the frame to send, p is the probability. Now we saw slotted aloha. This is as compared to that an unslotted aloha. In unslotted aloha, we do not have, we clear this, we do not have time slots, we do not have, these nodes who want to transmit sending at the beginning of the time slot. That's why the chances of collision increases. Why? Because in the slot when everybody knows that I will start transmitting at the beginning of the transmission time, and if a collision occurs, they would get to know that yes, it occurred because two of them sent at the same time. But in this case, somebody started sending, it will continue to send, but suddenly another one starts to send, even though the other one is about to finish. So this can create problems, and that's why we have here the efficiency lesser than that of the slotted aloha. Typically, it is said that the efficiency of pure aloha is half of that of slotted aloha. Here we have p into 1 minus p to the power of 2 into. So this means that it is even worse than slotted aloha. I'll just write here, efficiency of pure aloha is half of that of slotted aloha. I hope this is clear. Okay. The third category of a random access protocol that we have is carrier sense multiple access protocol. Now in CSMA, or let's see first, in both slotted as well as pure aloha that we just now discussed, it was decentralized in the sense that node decides to transmit. Yes. And it's independent of the activity of other nodes in the channel. They do not care about what others are doing, what others have to send. I have to speak, I'll start speaking. Ramanan has to speak, he'll start speaking. Regardless who are the people are in the class and who wants to speak. I do not pay to what Ramanand is saying. He doesn't pay attention to what I am saying. He is concerned with himself. I'm concerned with himself. I have to say something. I'll start saying. We start speaking at the same time. Collision happens. Then I will wait. He might wait. Both of us wait for a random time. Then we might have successful transmission. So Aloha protocols, both slotted and pure, are like people who continue to talk even though other people are talking. Does not follow people issue protocols here. Normally, there are two, rules for polite conversation. The first rule is listen before speaking. If someone is speaking, like I am speaking here, others would wait for me to finish, and then once I stop, the person starts to speak. So listen before speaking. The second rule for polite conversation that we have here is that if somebody else starts to speak at the same time when you are speaking, stop talking. Okay. Like here, it's given a human example is don't interrupt others. Two examples that I gave. The first one, I'll just write here. The first one that I just now mentioned is listen before speaking. If Ramanand has to speak something here, he first listens to what I am speaking. When I stop, so in other words, he is waiting for me to finish. When I stop, then Ramanand would start speaking. In network time terms, we call this as carrier sensing, which means that if a node has to start to transmit, it would first listen to the channel. How does it listen to the channel? It senses whether there is a transmission going or not. How does it sense it? Basically, there will be electrical pulses within the channel. If they are there, it will not send. We call it, it backs off. And it backs off for a random amount of time. Then what happens after a random amount of time? This random amount of time is basically a wait time. Like I'm speaking, Ramanand did not speak, then it says, okay, after a little while, I'll try to speak again. And after a little while, it comes back and sees I'm still speaking, then he again backs up. If I'm not speaking, there is silence within the class, Ramanand starts to speak. Similarly, in networking, the node senses the channel. If channel is busy, it backs off for a random amount of time. After that time is finished, it then senses the channel once again. If it's idle, it begins to transmit. Once it begins to transmit, others would again have it so that others can transmit. This is what we have listened before speaking. The second one that I mentioned just now is if someone is talking at the same time, so there is sensing, still someone is talking at the same time, stop talking. This part in networking is known as collision detection. This means if a transmitting node listens to the channel while it is transmitting, it detects that node is also transmitting and there is an interference or a collision that happens. It stops transmitting. And then using some protocol, it will start again after some time. A question arises here, okay? if I did carrier sensing, why do I still have to face collision detection? You can use your microphones to answer it. I'll give 1 mark for the correct answer. Anybody? It's 1 mark. It's a big prize. I repeat the question. Carrier sense multiple access says that we sense the carrier and then we send the channel, and if it's free, then only it sends. But still, collisions can occur. Why? Why do we need to have detection if we have carrier sensing? Nazish Khan says, because there can be delay. Very good. It can be delay. That is the answer of Nawazish here. Nawazish +1 for you. Good answer. See, this is channel. All right. This is a node. This is another node, and this is another node. We have here A, we have here B, and we have C. Now, we use CSMA in which we have collision sensing. At this specific time, there is nobody who is sending. Both A and C now want to send at the same time. Let's say A wants to send to B and C also wants to send to B. Now what happens during this time? It senses the channel and it's empty, no transmission. C also senses the channel and it's empty, no transmission. So both of them start to transmit at the same time, and they would detect the collision only after they collide, which will take some time. How much time it takes for transmitting would depend upon the length of the wire. All right, that is where we have PD, that is the propagation delay that comes because of the link here, and the propagation delay is proportional to the length of the channel. The more the nodes A and C are distant from each other, the more time they would take to send the, more time it will take to reach, more time it will take to detect that collision has occurred. So good answer. Propagation delay comes into play here. Even though we have CSMA, both of them sense it. It's like Ramanan and me. They want to speak. Both of them, we are quiet. Now I want to speak. Ramanan also wants to speak. Channel is empty. We start at the same time. This is what we have. So the two rules that we see here is CSMA, and in which we have carrier sensing, and the second one is collision detection, which just now I mentioned that if a transmitting node listens to the channel, detects that there is another one, there is interference, it has to restart again using some protocol. This we call as collision detection. One is simply CSMA. The second one that we have is CSMA-CD. I hope that's the answer. So here, collision can still occur because propagation delay means two nodes may not hear each other's transmission. Entire packet transmission time is wasted. Distance and propagation delay determining collision probability. So it's depicted here within this, that with respect to time, when this also sends, this also sends, what are the chances that we can have collision? The second one that we just now discussed, the CSMA-CD, in which we had the carrier sensing as well as collision detection. This depicts that. Then we have the example of Ethernet CSMCD algorithm. How it, I'll leave it for you to go through it. Okay. Find the efficiency of CSMACD as well, like we had the efficiency of the Aloha. You can compare its efficiency with performance of Aloha. And it shows that the performance here is better than Aloha. It's simple, it's cheap, and also it's decentralized. Okay. Yes, propagation. So longer the propagation delay, the answer is the longer the propagation delay, the larger the chances that the carrier sensing node will take, be able to sense the transmission during that time. This propagation time is the vulnerable time during which it can happen. Ethernet protocol that we have, CSMACD. Also, in addition to this, I will write here. Wait, okay. Do this as well, and I'll add one more thing that you would do here. Do persistent methods. And what are these persistent methods? What should a channel do if it's busy? So it uses persistent methods. There is one persistent method. There is non-persistent method. And also there is P persistent method. I'll leave it for you to discuss this. It's like one persistent. Link is idle, send immediately. No persistent. If link is not idle, wait for a random time. Sends again. If idle, send immediately. And so on. So I'll leave it for you to discuss. And the next and the third one that we have, probably, let me see how much we have more. We have taking turns protocol. Okay, we can finish it within today's class itself. Since we lost the last week, so let's finish it up. I won't take much of the time with these methods. Do we have any questions till now? Okay. So moving on to the next one that we have, the taking turns Mac itself taking the desirable properties that we had for multiple access protocols to have a throughput of R bits per second when only one node is active. And also with n nodes, what we had the throughput, it was divided by the number of R divided by the number of nodes that we had. With the previous ones that we had, like FDMA, TDMA, we saw that you divided it based on the number of nodes that he had. But the problem was that even though there is one active node, you still did not get R bits per second. But used Aloha and CSMA, which had the property that if there is only one node that is transmitting, it gets R bits per second. But the second one was not there, that if there are n nodes, we will get a throughput of R divided by n nodes. So
Channel partitioning had one of the property, random access had another property. That's why we have a third important protocol, that is taking turns protocol, in which it shares the channel efficiently and fairly at high loads. It looks for the both of the advantage pros of the random access as well as channel partitioning. And among this, we have the first one as polling protocol. What is polling protocol here? Polling protocol requires that we have one of the node designated as the master node. This is the one which I made the round. A master node polls each of the node in a round robin fashion. Like it says, it invites slave nodes. These are the slaves. It invites these nodes to send the data, typically used with dumb slave devices. So when it polls each of them, it will first message the node 1. Do you have anything to transmit? Master node tells node 1. If you have, transmit 10 frames now. So it can reply back, no, I don't have anything to transmit. So this is cleared. Master node goes to the second one and says, do you have anything to transmit? If yes, send 10 frames. Says, yes, I have to send, let's say 8 frames. It sends these, let's say it first has to send 20 frames. It sends the first 10 frames and then waits for the chance again. Then the master node goes to the third one, likewise fourth one, and back to the first one, and then goes to the second one, and second one has to transmit 10 more. It sends the next 10 within this. Now, after this, node 3 has to send, yes, it says I have to send, but I have to send 6 frames only. Master node gave a chance of sending 10 frames. So this is how actually poll happens. Now, one thing that was there, that if master node gives chance to third one to transmit 10 frames, but it had only 6 frames to send, the rest of the time is not wasted. Master node can determine when a node has finished sending the frame. How? Master node keeps an eye, or master node continuously listens to the channel. And when the master node sees that there is a lack of signal on the channel, so only 6 were sent, master node detected that channel is empty. Master node gives the channel to some other node, that is node number 4. At this instance of time, 4 would be sending the data. So remaining 4 slots during which frame could be sent are not wasted. That is an advantage here. So polling protocol eliminated collision, that was good. It eliminated empty slots as well. So it had a better efficiency. But with some advantages, obviously expect some disadvantages as well, like a polling overhead. What is polling overhead? That we would require each of the node to be notified whether you have to send or not. That is this thing. That is the time that it takes here. This one. See, polls it, sends back the data, polls it, sends back the data. So we have a polling overhead. And what does this polling overhead mean? It means that we have a polling delay. And what is this polling delay? It's the amount of time which is required to notify a node that it can transmit. That was this signal that was just now sent. This is latency, this is a delay which is introduced with it. And also it is centralized. We have a master-slave relationship. And if master fails, the whole of the system, the whole of the MAC protocol of taking turns fails. The thing is, if only one node is active, node will be transmitting at the, I mean, it's actually a con. It's a disadvantage that even though among these four, if only one node is active, node cannot actually send at R bits per second. Why? Because master node has to poll each of the inactive nodes in turn. Each would take a time to reply, no, I don't have to send anything. The polling delay, that is to be added. So if one has to transmit, master node gives the chance like one has to transmit, let's say 50 frames. It gets chance of 10 frames first. Then master goes for round robin fashion, polls others. Others do not have to transmit, but it has to go and ask them whether you have to transmit or not. That polling delay of each node would be added, and then it goes back to the first one. So these are the advantages and disadvantages we have for taking turns protocol. So the next one for taking turns protocol after polling protocol is token passing protocol. It's shown in the figure here. Not have any master slave relationship. They are all, let's say, in a ring fashion, in a circular fashion. The first one has nothing to send, all right? And let me go back. This, you can see here T. This T denotes a token. It is a small special purpose frame known as token, which is exchanged among the nodes. And it is exchanged in fixed order. Like for example, in the class, I have to give chance for everybody to speak. Okay, I give I do not actually control the class. You among yourself are there to speak. You make a card, a green card, and then pass this green card from first bench to second bench in some specific order. Whoever has this green card knows that I have the chance to speak. Now, if I have nothing to speak now, I will pass on this green card to my person who's behind me in order. If I have to speak, I will keep this token and start speaking. That doesn't mean that I have the token and I'll keep on speaking. I will keep this token. I can speak for a specific amount of time. Once that time is finished, I know as protocol, I pass on this token to the other one. So there's nobody as such who controls this token. It's a decentralized system here. Likewise, when node 1, 2 here, node 1 has to send, it sends the token to the next one. The next one has nothing to send. So what it does, it passes on the token to the next one. The next one has some data to send, it sends the data. After completing the transmission of data, it passes on the token to the next one, and so on. And it's not that if this PC has this token, it will continuously keep on transmitting the data. No, it will transmit only for a specific amount of time that has been given to it as per the protocol. Advantages what we have with token passing. It's a decentralized system, no master-slave relationship. It has higher efficiency than what we have in the previous one. But it has some drawbacks as well. A small token overhead is there, passing of token is there, that introduces a certain latency. And also, it can be a single point of failure in case the node that has token fails, not the other one if other one fails. It's like in the class, Ramanand got the green token and he got a call and he went out of the class and he took the token with him. And others are waiting. And he forgot and he left back, he went to lunch with the token itself. So the channel is crashed here. It can happen that within this ring that we have, the one which has the token can crash, and because of that the whole system can crash. But what happens in those cases? In those cases there is a mechanism for failure which is known as a recovery protocol, and recovery protocol is initiated which generates the token once again and it to move as it. Okay, it doesn't mention a third one here, so I have to put in the third slide. After the taking turns, I had mentioned the third one, that is the reservation protocol. So let's discuss the third and the last one. The reservation protocol is a type of taking turns protocol, which is a subcategory of random access protocols. And in this case, what do we have here? We have reservation system in which a station needs to make reservation first before sending data. Next, time is divided into intervals, and in each of the interval of time divided, a reservation frame is first sent or precedes the data frame that is sent in that interval. So if there are n slots, we will have exactly n reservation mini slots in the reservation frame. So it's like this. Let me draw it to make it explain, make it simpler. So, okay, now we have these small ones depicted here. They are what we call as mini slots. And we have a bigger slot that is here. In this, we will be sending this is the data station 1. This is the data station 2. Then again data station 1. So let's try to understand it. Each mini slot belongs to a station. When the station needs to send a data frame, it makes a reservation in its own mini slot. So it will say here 1. The rest of the station, if there are 3 sending ones, they have 0, 0, 0. If there is station 2 sending, we have 1 here. The rest of these would be 0 and 0. So in other words, when a station needs to send the data frame, it makes reservation in its own mini slots. After that, it can send the data frame as simple as this. In which you mentioned that yes, I am be sending, this is my mini slot, I'm reservation, I will be sending the data. And this time is divided as per the time slots. I think that should be it for today. So we have done with this multiple access protocol. This is a cable access. This is the summary, the 3 that we did: channel partitioning, random access, and the taken time. In our next class, we will be taking the MAC address and resolution protocols. Both are important. We'll be discussing about the frame structure as well. And also, an important is routing in the data link layer, how we send the data across. And hopefully in our next class, we'll finish the data link layer. Any questions? Yes, any questions? I hope you understood I hope things are clear in the class. If no questions, then I'll stop here and I'll see you in the next class. Right, Ramanand, please upload this in the group as well as on the YouTube, and then we'll discuss about the dates for assignments as well. Regarding the lab, just confirm if everybody has installed it. So by Friday, hopefully we should be able to take at least our second lab, right? Okay, I'll stop here. So I'll see you in the next class.